So this chapter 2, chemical organization of life, can have, so we look at the level of organization, how atoms form um, molecules from macromolecules from organelles, organelles from cells from tissues from organ system, and organ system organisms. Now, so here we are looking at the chemical level of organization. We're looking at the chemicals. So we're looking at the atomic level, molecular level, macromolecular. So those are the chemical level of organization. Now, it's imperative to know that all organisms, including you, are made up of matter. All right. And matter is anything that has mass and occupies space. So whatsoever it is that you can categorize as having mass and occupy space is a matter. Now, matters are made up of elements. And elements are the hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon, potassium, and calcium. Those are the first 20 elements. All right. Now, those elements makes up the matters. And the elements are made up of atoms, which I'm going to be talking about soon. So when elements react together, they form molecules. Then compound is formed through that. So compound formed from elements. All right. Now, so sodium is an element, chlorine is an element. Sodium chloride will be a compound, right? In this case, an ionic compound. We'll talk about that. And so, um, among all the elements that are known, about 20 to 25% of them are very essential, uh, because essential in that they are needed by an organism to live a healthy life and reproduce. Now, those are essential elements. Those are elements that organism cannot do without. Then we have some elements that, even though they are important, but they are required in trace amount, very small quantity. An example of that is iodine. Now you know that you have iodine in some salt. So you have iodine salt, and that is actually the only source of iodine that we eat. All right. That's iodine. Now, iodine is very important in metabolism, very important in the thyroid function. If there is any problem with iodine, deficiency of iodine lead to goiter. However, it must be consumed in minute quantity in a very trace amount. Now, so natural occurring elements are actually toxic to organism. So like arsenic, for instance, now is traceable to many diseases are traceable um, to arsenic, and it is also poisonous, can lead to death. Some species have become adapted to the environment containing elements that are usually toxic. Now, if you look at sunflower plants, they are able to now take up lead, take up zinc, and heavy metals um, in concentrations that are usually toxic, that can destroy organisms. All right. Now, I told you that elements are made up of atoms. And so we'll be looking at what actually makes up an atom. Atoms are dominated by three subatomic particles. We call them subatomic particles. The first one is the neutron. Think about neutron as neutral, no charge. Then the second is the proton, then electrons. Electron is negatively charged, proton is positively charged. So when you come here, in the nucleus, you have the proton and the neutron, and surrounding around it, revolving around it, is the electron. So neutron and proton form what we call the atomic nucleus, and that's what determines the mass of an atom. So the mass of an atom is determined by proton, and neutron inside the nucleus. So how about electrons? Electrons do not have mass. The mass of electron, even though it is quite insignificant. It's 0.0000 something. So it is very insignificant. What determines the mass of an atom is the neutron plus proton proton. So atoms of various elements differ in number of subatomic particles. We'll talk about that. An element's atomic number is the same as the proton number. So atomic number is the number of the element on the periodic table, and that is the same as proton number. Now, when you add neutron plus proton, that becomes atomic mass. All right, atomic mass or mass number is simply proton plus neutron. So atomic mass is the same as mass number, and that is equal proton number plus neutron number. Right? So when you add those two together, that's what gives the atomic mass. All right, and I told you the mass of an element of an atom is not determined by the electrons. All right, so when you look at this is sodium ion, sodium, and this sodium, you see the atomic number is 11 and the mass number is 23. So how did that come to play? The mass number, the proton number is 11 and the neutron number is 12. That's how we came across 23. So neutron number is 12, proton number is 11. Now, you see, because neutrons and protons have a mass of approximately 1 Dalton, we can estimate the atomic mass of sodium as 23 Dalton. Now, what do we call isotopes? I told you that what makes up the content, the mass of an element, of an atom is the neutron plus proton. Now, there are times, even though proton of an element is constant, but the neutron can vary. All right. There can be neutron there can be an element variation with different neutron number. All right. When the neutron number is different, so when an element has the same proton number but different neutron number, we call those elements isotopes. So isotopes means the same proton number but different neutron number. So that means the element is the same because what determines the characteristics of an element is the proton number. So isotopes are two atoms of an element that have different neutron number. All right, so radioactive isotope decay spontaneously giving off particles and energy. Some of its application is in dating fossils, in tracing atoms through metabolic processes, and in diagnosing medical disorder. All right, now energy level of electrons. The energy is obviously the capacity to work, to cause change. Now, potential energy simply means the energy that a matter has because of its location or structure. So that means when it's at rest, energy at rest is potential. And if you look at the word potential, it means it has the ability to dissipate the energy, but it is still there uh, unexplored. The electron of an element defines the amount of potential energy, obviously, and changes in potential energy is going to occur in steps of fixed amount. Now, an electron's state of potential energy is called its energy level or electron shell. So I'm going to show you that now. Now, look at this. So I told you that mass number is determined by proton number and the neutron number, and those are located inside the nucleus. All right. So what we call shell is simply formed as electrons which are negatively charged revolve around the element, around the nucleus. So now here you have the nucleus here. So here you have a nucleus here. and there's proton and neutron inside this nucleus. Now, electron is going to revolve around this like this. Electron will keep revolving around it. Now, the first revolution that you have is what we call the first shell. And the first shell of electron only have capacity to accept 2 electrons. Now, the second shell is a higher shell. It has capacity to receive 8 electrons. Then we have another shell that has capacity to receive electrons. Now, aside from the 2, the first shell, so you see electrons are found in different electron shells, each with a characteristic average distance from the nucleus. The energy level of each shell will increase with distance from the nucleus. So I'll talk about that. Now, electrons can move to higher or lower shell by absorbing or releasing energy respectively. Now, so as you can see here, this shell contain different capacity of electrons, and I'm going to talk about that as we go. Now, look at this. This is electron. This is at a periodic table showing you how the elements are arranged and how they are dispersed and organized in the periodic table. Now, one of the things I need you to take note here before we go is this. The position that an element is in the periodic table determines a lot about it. It determines its feature, it determines its characteristics, it determines a whole lot about the element. So all we need to know the properties of an element is to know its number on the periodic table. Now, chemical behavior of an atom depends mostly on the number of electrons in the outermost shell, which we call valence shell. And I'll talk about that. Now, valence shells are the shell, the last shell, the outermost shell that the electron makes over an the valence shell is the last shell, the outermost shell that the electron surrounds um, on an element. Now, that is actually what determines the reactivity of an element. So the more reactive an element is a function of its valence shell. Now, I will talk about this later and it will make very much sense to you. But when you have an element that has, let's say, like carbon, for instance, now, or so oxygen, for instance, as I'm going to check if I have a now oxygen, for instance, or let me use this chlorine now, as it were, have 17 electrons. And so if you check here, the first shell here contains 2, you can see. The second shell contains 8, and the last shell contains 7. That is 17. Now, how do we know how reactive chlorine is going to be? Chlorine is going to be reactive based on the way its outermost shell is. When the outermost shell is full, we say chlorine is stable. When the outermost shell is not full, then it's not stable. So ideally, since it is 2H7, 2 on the first shell, 8 on the second shell, and 7 on the third shell. The third shell is supposed to contain 7. So that means it is not stable. Because for it to be stable, the shell must be full. So either the shell is 1, it's unstable. Either the outermost shell is 2, it's unstable. Either the outermost shell is 7, it's unstable. It's only stable when it contains 8, or when it is absent. All right. Now, so that is that. Now, the more unstable an element is, the more reactive it becomes. All right. So the reactivity of an atom arises from the presence of one or more unpaired electrons in the valence shell. So what is the number of electrons that are unpaired in the valence shell is what we are looking for, because that's what is going to help in bond formation. All right, so what we call chemical reaction is when elements that are that are unstable react together to form chemical bonds, and so they become bonded together. So be looking at the kind of bonds that are formed in chemical reaction. So the first one I'll be looking at is a covalent bond. Now, covalent, from the word covalent. Now, I just told you the valence shell is the outermost shell of an atom, and what determines the reactivity of the atom is the quantity of electron in the outermost shell. An outermost shell that have 8 electrons is full, and that will not allow chemical reaction. All right. Now, so since our reactivity is based on valency, so covalence simply means how they share electron in their valence shell, or how they share their valence electron. So a chemical bond is the sharing of a pair of valence electron by two atoms. So what is key here is the sharing. Now, covalence cooperates. Co means sharing, is to share electron. All right. Now, so if you see, looking at this now, you have this is hydrogen molecule. This is hydrogen molecule. By the time they join together, it's going to form, hydrogen atom, hydrogen atom. By the time they come together, they're going to form hydrogen molecule. This is sharing. Now, it's sharing because when you see this guy here, it was unstable. This guy here has now become stable. Um, all right, so covalent bond simply means sharing the valency, right? So it's when bonds are formed, and for a bond to be formed, 2 electrons are required. Now, there are 2 kinds of covalent bond which I'll be talking about. There's polar covalent bond and there's non-polar covalent bond. Now, covalent bond just join 2 atoms together to form a molecule. So it's a is a bond that requires sharing of electrons between 2 non-metals. All right. Now, this is an example. These are examples of covalent bond. As you can see here, you see hydrogen atom. Let me use the annotation. So here you see hydrogen atom, right? This is an hydrogen atom. This is another hydrogen atom. The two combine together because ideally hydrogen is going to be like this. This is going to be an hydrogen molecule. Then there's going to be an electron here, then plus another hydrogen molecule with an electron here. Then both of them are now going to form one hydrogen molecule together by bonding together. So we are now going to have this is one forming the bond. Now, the idea of this is that whenever you see this new hydrogen molecule, if you are looking at this from this side, it will be that this first hydrogen molecule have complete electron in its first shell, which is 2, because this has 1 electron in its first shell, so it's unstable. And why do why are atoms, elements involved in chemical reaction? Is to maintain stability, right? Now, so when you look at this is actually unstable because in its outermost shell is going to be just 1 electron. And the other one in its outermost shell is going to be 1 electron. But now they're going to join together as such so that when you're looking at this, just like what you're seeing here now, when you're looking at this one, you're going to see it as though it has 2 electrons. When you look at this one as well, it's going to show that it has 2 electrons. So at that point, they become stable by sharing together. So it's as good as you have food, I have water, and we decide to come together and eat the food together and drink the water together. We have both shared equally. That is sharing, right? So they share to maintain stability. So since two electrons are required to make a bond, so one bond is formed here, and that is called single covalent bond. This is a type of um, non-polar covalent bond. I'll still show you that. Then the same thing oxygen, but oxygen is actually number 8 on the periodic table. So it's going to be 2 electrons on the first shell, then 6 electrons on the second shell. All right. So by the time you have the second shell is going to be like this. Let's say this is the second shell. You have 1 electron here, 1 electron here. You have another electron here, another electron here. That's 4. Another one here, 5. Another one here, 6. So what's going to happen is now there are 2 electrons in the outermost shell. So this electron is going to bind to 1, this electron is going to bind to 1, and that's how you have 2 oxygen coming together, because they are both going to have this, and then both of them can join together and form a molecule. And that's what is going to produce O2. So this is what we call H2, which is hydrogen gas, and this is O2, oxygen gas. All right. Now, these, I'll talk about this. Now, this is a kind of, so we can also have triple covalent bond, which is what happened in nitrogen. Now, this is what happened, this water molecule, you will notice that ideally when you see this, both of them are beside each other. Looking at this, they are at angles to each other. Looking at this, they are beside each other. But this, the hydrogen cannot just stay in a balanced relationship with water, with oxygen. Now, why is that happening? This is a kind of sharing that even though they are sharing and they are both sharing, but one person, one element likes likes electron more than the other. So oxygen likes electron more than hydrogen. So because of that, even though they are sharing, the sharing is not going to be equal, it's not going to be even, because oxygen likes electron more. All right. Now that's going to be the case of if we have to share something together. Let's say you have to share fries, and you like fries more than myself. That means you are going to eat more fries than myself, even though we are sharing. The sharing is not going to be equal. All right, let's go. Now, this is what I was talking about electron. So atom in a molecule attracts electron to varying degrees. There are different level of attraction to electron. Electronegative elements are going to attract electrons more, and that is where oxygen falls into. So the more electronegative an element is, the more strongly it will pull electrons when needs be. Now, so we talked about non-polar. Non-polar is when two molecules come together, they share equally. So it's not moving to one pole than the other pole, it's just equal sharing. Then the polar is when it draws to one side than the other. That is an unequal sharing, which is what happened in water molecule. Now, the other kind of bond that we have is a ionic bond. Ionic bond is the scenario you see here, which is very interesting. All right, so when you come here now, you see this is sodium, and sodium is number 11 on the periodic table. So you see on the first shell, there's going to be 2. I'm going to clean this. So on the first shell, yeah, there are going to be 2 electrons because it's 11. On the second shell is going to be 8, and the last shell is 1. And chlorine is number 17 on the periodic table. The first shell is going to be 2, the second shell is going to be 8, and the last shell is 7. Are they stable? No. They are both unstable. And that's why they both want to react with each other to maintain stability. All right. Now, well, looking at this, which one is, I was asking my student this morning that if you have $50 and I have $250 and it's only $300 that is required to register for a class, I said, who should register for the class? Who is fair? Who should register for the class? I should, because you should borrow me your $50 and not that you should collect my $250 to add to your $50. I should take my $50, your $50 and add it to my $250. And so that's the way this is. Now, so sodium has one on the valence shell, whereas chlorine has 7 on the valence shell. It is just right that sodium will transfer its 1 to the 7 in a way that both of them will now become stable. Do you know what? This will lose this shell, and these will now have become 2/8. So in that case, sodium has lost a shell. I mean, lost an electron. When you lose an electron, you have lost negative. It's like you paid your debt. So you have actually become Na plus. So this will become Na plus, whereas this is going to become Cl minus. So the idea is this. Anywhere we see Cl minus, we know that this is a chlorine that has borrowed an electron from somewhere. Anytime we see Na plus, we know this is a sodium that used to have 11 electrons, but now it has given out some of its electrons. So that case, it has become positive, saying that I used to have it, but I've given it out. I lost my negative, meaning that it became more positive. All right. So that reaction is actually what we produce. You see Na plus and Cl minus, which will give rise to NaCl. When it is positive, we call it cation. If it is negative, we call it anion. But generally, those are called ions. Because the reaction is formed based on ions, we call it ionic bond. All right, so this is a cation is positively charged molecule ion. Anion is negatively charged. Ionic bond is a bond formed between a metal and a non-metal, which is an anion and a cation. Then complete compound formed by ionic bond, we call it ionic compound or salt. And salt could be sodium chloride, it could be table salt, as the case may be. Now, weak chemical bonds. Now, weak chemical bonds, most of the strongest bonds in organisms are usually covalent bonds. And I'll talk about some weak covalent bonds as we go. Now, hydrogen bond is a force of attraction, and that is the bond between water molecules. So this is one water molecule, and this is one water molecule combining to ammonia through hydrogen bond. Now, if two water molecule also is going to combine, it's going to combine through hydrogen bond. Now, this is water molecule. When you see water molecule, what do you notice? They are usually together. All right. Okay, I'll talk about that. Now, they are usually called together, and their togetherness is because hydrogen bond binds them together. So hydrogen bond forms when a hydrogen atom covalently bond to one negative atom, which can be oxygen in the case of water, or it could be ammonia in the case of, it could be nitrogen in the case of ammonia. All right. Now, van der Waals interactions. Van der Waals interactions are usually, if electrons are distributed asymmetry in molecules or atoms, they can result in hotspot of positive and negative charge. I will explain that. Now, weak van der Waals attractions happen between molecules that are closely related together. All right. Now, they are force of attraction. They are interactions. So what you see is you see the gecko toe hairs and the wall surface. That is just wall of attraction. It's different from the bond. It's just force of attraction, just closer to what you see in hydrogen. Now, molecular shape and function. Now, you have learned that structure determines function, that the structure of a thing determines the way it functions. All right. Now, let's go. Now, like I told you, so oxygen binds to hemoglobin, and hemoglobin is the protein that carry oxygen. Once there is a problem with the structure of hemoglobin due to a mutation, what is going to happen? That hemoglobin, we say it is now sickle cell anemia, because anemia means deficiency of oxygen. And so as such, that kind of that hemoglobin that has been affected, either mutated, will no longer be able to do the function it should perform again because of the change that has happened to the shape. All right, no, chemical reaction simply means when molecules or elements come together simply to attain stability, that is what leads to chemical reaction. And it's simply when the point when they come together and a bond is formed between them, that is what we call chemical reaction. So if there's going to be chemical reaction, there will be at least be a product, a reactant, which will lead to the product. All right. So here are the reactant here. This is 2H2 plus oxygen molecule forming 2H2O. That is reactant forming product. Now,